Remind me later. Sorry. Okay, there we go. What do you think? Are we ready to go over it, or do you want another minute? Anyone want another minute? Okay, take another minute. Okay, what is the definition of kinetic energy? It's energy of motion, yes. Now, I didn't ask you this, but does anyone remember what the motion of the particles is? There's 3 types. Vibrational, rotational, and translational, yes. Now, let's look at what each of these types looks like, okay? And you can actually do a couple of them with me. You might need to stand up though, okay, at some point. Okay, so first of all, we're going to do vibrational. There's a few types of vibration. There's side-to-side vibration. So you can imagine if I am a CO2 molecule, the middle of me is the carbon, and then here's the 2 oxygens. Asymmetric stretching. Do it with me. This is vibration, okay? There's also symmetrical stretching. Okay, that's another form of vibration. And there's also, see, good exercise in the morning. Aha, okay. So those are vibration. Now, at the same time as a molecule can vibrate, what else can it do? It can also, yes, but at the same time as it's spinning, it can also be moving. Oh my God, okay, I'm not gonna do that anymore because it's making me dizzy. But, so that is translation. Translation is when it moves through space. All right, so those are our 3 types of molecular movement. All right, now we want potential energy. What is potential energy? Stored energy, yes. And if we have high potential energy, is that stable or is that unstable? That is unstable. And low potential energy is stable. Okay. What was our next word? The law of conservation of energy. What is the law of conservation of energy? Energy cannot be created nor destroyed. Only transformed, yes. Now, when we say this, sometimes this gets a little confusing because sometimes we say that the system is losing energy, and the system does lose energy, okay? But it's not like the universe doesn't lose the energy, because if I've got a beaker and in it is the reaction, the reaction is the system. If it loses energy, that energy can move out of the system and into the surroundings. So the total energy of the universe is staying the same, but the energy of the system is decreasing. Does that make sense? Okay, so total energy is equal to the kinetic energy plus the potential energy. Okay. Energy can also move into or out of a system. And the system is the reaction that we are observing. The system can lose or gain energy, but the universe does not. Can lose energy to the surroundings, or gain energy from the surroundings. But the universe, which is the system and the surroundings, the total energy remains the same. But in the universe, the total energy remains the same. I can also print this out for you if you're having trouble keeping up with it, okay? Because I know I have many injured people. Okay, what was our next question? That was 3, what's number 4? Temperature. What is temperature? Average kinetic energy, yes. So if the kinetic energy increases, what happens to the temperature? Temperature increases. And if kinetic energy increases, what happens to the speed of the particles? Yeah. So that, yeah, you should remember that those 3 things go together. If the kinetic energy is increasing, the temperature is increasing, the speed of the particles is faster. Conversely, if kinetic energy decreases, the temperature decreases, and the speed of the particles, is slower. And if you're taking notes at university, being able to just go ditto, ditto, ditto for something that's right above it makes your life easier because it makes it faster. Yes? Okay. Now, number 5, we were going to fill in some blanks. I'll wait for you to be done with that. Okay. Like I said, I will print it out, so if you missed any of that, it's okay. All right, in an endothermic reaction, what kind of energy enters the system? Kinetic. Kinetic energy enters the system. You can think if you have this beaker and there is a flame, yes, that flame is making the molecules touching the bottom It's making them move faster. So that kinetic energy is now going into the system. So it enters the system and is transformed into what type of energy? Potential energy. Because kinetic energy decreases, because we've taken kinetic energy and transformed it into kinetic energy. I should write that as lowercase because it looks weird otherwise. Because kinetic energy decreases, the system will feel cooler. So this is the weird part. Endothermic is really almost a little bit more difficult to understand because you're like, well, there's a flame, yes? So it feels hotter. Is that heat, though, is that increase in temperature coming from the system or is it coming from the surroundings? It's coming from the surroundings. So you have to think, this reaction is actually cooler than it would be if I were to just heat, like, say, air, right? And it didn't do anything. You know what I mean? So if I had, let's say I had an endothermic reaction where I did not have to heat it, which is less usual, but you could have it happen. It would take kinetic energy, say my finger was touching it, it would take kinetic energy from my finger, from the molecules in my finger, and it would transform it into potential energy. What would my finger feel like? The molecules in my finger would get slower, right? Because the kinetic energy is moving into the system and being transformed into potential energy, right? So you can think the molecules in my finger are bumping around, like they're jittering, right? And so there's transfer of heat from my finger into the beaker because my finger molecules are bumping into the glass molecules, which then bump into whatever is inside the beaker. Yes? And then that extra energy from my finger is now being used in the chemical reaction and transformed into energy that is stored in chemical bonds. So now we have higher potential energy, but the particles in here are moving slower, and so it's like it's sucking kinetic energy out of my finger. That's the easiest way to think about it. Don't worry about it, I'll put it back in. The easiest way to think of it is sucking kinetic energy out of the molecules in my finger and transforming it into potential energy in the reaction, which is why my finger then feels cooler, because my finger molecules have less kinetic energy, so they are moving slower. And if things are moving slower, they feel cooler. Okay, in an endothermic reaction, the potential energy, does it increase or decrease? It increases because we took in kinetic energy and we transformed it into potential energy, so the potential energy is getting greater. Okay? So now that we have talked about that, let us go to your blue book. No, your ivory book. Ivory book. And we are at the bottom of page 100. So let's say that our reactants have 2 kilojoules of potential energy. Okay, I'm going to draw my potential energy in blue. Okay, 2 kilojoules of potential energy are stored in my reactants. Are you with me so far? Just because of the nature of those reactants, inside them they contain some potential energy. Just like if you have a hamburger and you eat it, the chemicals in the hamburger contain energy that can be released as your body digests it, yes? So like sugar contains energy, and as your body digests it, it will release that energy. So every chemical has some amount of potential energy in it, and these reactants in this particular example have 2 kilojoules of potential energy stored in them. Our products, on the other hand, have 12 kilojoules of potential energy. How did we go from having chemicals as an arrangement of atoms? We rearranged those atoms in a different way because that's what a chemical reaction is. It's a rearrangement of atoms. All we did is we rearranged them, and all of a sudden we've got 10 extra kilojoules of potential energy. Where did that potential energy come from? Chat with your partner. Where did it come from? Ten kilojoules of kinetic energy comes into the system from the surroundings. And then what happens to it? The chemical reaction then transforms that kinetic energy into potential energy. So now we have 10 extra kilojoules of potential energy. If you don't get this year, it's okay. We're going to do it again in grade 12 next year. The reason we're doing it twice is because it's one of those things that can be a little like googly on the brain. And if you don't know what like googly on the brain means, then you're smarter than I am, because many things are googly on my brain the first time I learn them, okay? So this is just kind of showing you that before the reaction, our total energy, we have our potential energy, 2 kilojoules, 12 kilojoules of potential energy, and then we had our 10 kilojoules of kinetic energy. And so the total energy before the reaction is the same as the total energy after the reaction. And if you go on to study chemistry at university, you can actually look up tables to find how much energy is contained in the reactants based on what their bonds are, okay, and things like that. But we're just going to show this graphically at this point. We are going to put our potential energy on the y-axis, so that is our potential energy. And if you want to label it potential energy, it's actually in kilojoules per mole, although you'll sometimes just see it as kilojoules. Now, I don't like this diagram. This diagram makes me sad. I need to fix it. And the reason is that we see our potential energy increasing, but it is starting where it should, because the potential energy starts at where the reactants were. It starts at 2 kilojoules, and it does not finish here. Yes? That's why that diagram makes me unhappy. Where does the potential energy finish? Up at the product. So if you could extend that arrow, please, because when you do a quiz or a test on this, I will expect your arrow to go from the reactants to the products. So it must touch the potential energy of reactants and the potential energy of products. So I need to fix this resource. I was very distressed when I found out I had not done that. Okay. So this kinetic energy here, what is it doing? It is entering, yes. From where? From the surroundings. And then what happens to it? Tell your partner. After it enters from the surroundings, what happens to it? It is transformed into what? Potential energy. Excellent. So kinetic energy comes in, it's transformed into potential energy. Therefore, what happens to the temperature? Yeah, therefore the temperature decreases. Why is temperature decreasing? Because temperature is the average kinetic energy. So if KE decreases, temperature decreases. Is good? Okay. So this is an endothermic reaction since kinetic energy has entered the system and has been transformed into potential energy. We are going to leave it for now and come back to it tomorrow because I feel like this is something that your brain can process better if you do it over several days. Okay, and we are going to move on to Unit 7. So your blue book, please. Stoichiometry. Now, I know you guys all watched the video and or read this. Okay, you'll notice that there is a pronunciation guide, stoichiometry. So this is page 4. We're not going to spend a lot of time on this because you've already done it. Yes? But we have just done a unit where we've been balancing chemical reactions, yes? And when we balance chemical reactions, we have the various chemical species. So for example, this CH4, how many CH4s are there? There are 1. How many O2s are there? There are 2. And how many CO2s? 1. And how many H2Os? 2. Those coefficients are going to be super important because you can make conversion factors between 1 CH4 to 1 CO2. Yes? You could do a conversion factor between 2 O2s and 1 CO2. You can do a conversion factor between 2 H2O and 1 CH4. You can do conversion factors between any of those. Yes? And it doesn't just work for molecules. Are we okay with the concept that it scales up to pairs of molecules? The ratio remains the same. It scales up in the same way the ratio remains the same. 1 particle to 2 particles mean 1 dozen particles to 2 dozen particles. And finally, we can scale all the way up to a mole, where we have 6.02 times 10 to the 23 CH4s. Here we have 12.04 times 10 to the 23 O2s. We have 6.02 times 10 to the 23 CO2s. And we have 12.04 times 10 to the 23 H2Os. Is good? Okay. Did we have any problem with the exercises? No. I'm not sure that I love this page because I find it's a little overwhelming, but let's just take a quick look at it. So this ratio here, this one, we have N2 plus 3H2 gives 2NH3, so we have a 1 to 3 to 2 ratio, and that works for individual molecules. You have 1 molecule, 3 molecules to 2 molecules. It also works for moles, 1 mole to 3 moles to 2 moles. Now, do you remember gases? What do we know about gases? At the same temperature and pressure. Do you remember? Equal number of particles take up equal amounts of space. So we can say we have 1 mole of N2, which is 22.4 liters, yes? And we can have 3 moles of H2, which is 22.4 plus 22.4 plus 22.4, okay? And we have 2 moles of NH3, so that ratio, hey, look, we still have a 1 to 3 to 2 ratio. So the ratio works for molecules, the ratio works for moles, the ratio works for volumes of gas, as long as they're all at the same temperature and pressure. What does the ratio not work for? It does not work for grams. We have 28 to 6 to 34, which reduces our lowest terms for grams are 14 to 3 to 17. Is that the same as 1 to 3 to 2? No. So you cannot use that, the ratio of coefficients, to convert from grams to grams. Okay? So what we're going to be learning about, and what you have already started learning about, is this little bit in the middle. Most of the time what you're going to do is you're going to take the moles of A and convert it into the moles of B. And you will use a mole ratio, but this time the mole ratio is not the ratio within the compound, it's using the coefficients from the balanced equation. And what does that work for? It works for molecules. What else does it work for? Moles and liters of gas. So the ratio of coefficients the mole ratio works for molecules, it works for moles, and it works for liters of gases. Thank you. That's okay, I'll just take those. Yeah. Is good? Okay. So hopefully we've done these calculations. If you have questions about them, come in and see me. We are going to move on to 7.1b. And we're going to be looking at the mole ratio. This is on page 9. Okay, page 9. And guess what else we're going to be using from our mole unit? We're going to be using molar mass. Where do we find the molar mass from? We find it from the periodic table. We might need to use Avogadro's number, okay? And remember, the one goes with the mole. One goes with the mole, okay? Mole. And we might need to use molarity. What type of substance would we be dealing with if we're using molarity? That would be aqueous, so that would be solutions. Yes, of course. Okay, and for all of these calculations, if you're going from substance A in a reaction to substance B in a reaction, you must convert through the mole. Now that's a little bit of a lie because you can go from the number of particles to the number of particles using the ratio of coefficients as well. But if I give you moles of A, you can convert directly to moles of B. But if I give you mass of A and you want mass of B, what do you have to do first? You would need to convert your mass of A into moles of A, and then moles of A would have to convert to moles of B, and then moles of B would have to convert to mass of B. All right. So here we are. The combustion of propane, C3H8, plus 5O2 gives 3 CO2 plus 4 H2O. And if we ask ourselves what mass, so that's the number of grams of CO2, so that's where we want to finish. That's why it says, what does it say over here? That's where we want to finish. And we want to finish with CO2 is produced by reacting 2 moles of O2. So if CO2 is substance B, that means O2 is substance A. So we're starting with moles of A, which is O2. And we want to finish with mass of B. So we have to convert first from moles of A to moles of B, and then from moles of B we can go to mass of B. Okay, so do you think you could do that? Could you do that? I forget, is it actually written here for you? It is, but what if we did it together? We could say, I want to find the grams of CO2. And I'm starting with 2 moles of O2. if I have moles of A, I can always convert to moles of B, which will get me closer to grams of B. So we need to cancel moles of O2 and find moles of CO2. Where do I find the numbers that go in there? Those numbers are going to come from the coefficients in the balanced equation. So let's go back to our balanced equation and say, what's the coefficient for CO2? The coefficient is 3. What's the coefficient for O2? It is 5. Okay, that gives us moles of CO2. And then what would we have to do? We want grams of CO2. We know how to go from moles to grams. What conversion factor do we use there to go from moles to grams? We use the molar mass. And where do we find the molar mass? On the periodic table. Carbon is 12.0, oxygen is 16.0, 2 times that is 32.0, so that is 44.0. Don't forget your 0.0 grams per mole. So now we have 44 grams of CO2 per mole of CO2. And now that we're in stoichiometry, you always want to write your chemical species because they're going to keep changing. Yes? Right? We now have a new chemical species. So this unit, you want to make sure that you do write down what you have moles of. Okay, sometimes in the last unit it didn't matter so much, but this one it does. And we can do our calculation and we'll get 58.2, hurrah. Okay. Now, let's pretend there's no map here. If I want to start with 100 grams of H2O, and I want to finish with what mass of C3H8, I want to find the grams of C3H8. What would I first have to do with the grams of H2O? Convert them to moles, because if I want to go from H2O to CH3, I can only go through moles, because I can convert moles of A to moles of B. I cannot convert grams of A to grams of B. So let's convert to moles. So that's going to be moles of what? H2O. And then from moles of H2O, I can convert to moles of the other thing that I want, moles of B. So that's moles of C3H8. And then we can find grams using our molar mass. Okay. So grams to moles, moles, grams. So we're going to start with 100 grams of H2O. We want to cancel grams of H2O and find moles of H2O. I happen to know the molar mass of water. Anybody else know the molar mass of water? It's 18.0, and if you don't know that, that's okay. You can go and add them up. That works just fine. Now we have moles of H2O. We want to get to C3H3. Does this say C3H3? Should be 8. That should be an 8. Okay, and so we now need to, absolutely, yeah. So now we need to cancel moles of H2O, and what are we trying to find? Moles of the other thing. So we're always converting into moles first, and then we convert into moles of the other thing. So the first two steps are always the same. Find the moles, find moles of the other thing. Step 1, find moles. Step 2, find moles of the other thing. What's step 1? That was so sad. I had one person. What's step one? Find the moles. What's step one? Find the moles. What's step two? Find moles of the other thing. What's step one? Oh my God, no, everybody, what's step one? Find the, what's step two? Find moles of the other thing. Okay, good. So we found moles. Look at us go. We found moles. Now we need to find moles of the other thing. What is the other thing? C3H8. Where do we find those numbers? Yeah, the numbers come from the coefficients. And what's in front of C3H8? Way back up at the top. C3H8, there's a 1, and water, there's a 4. So C3H8, there's 1, and H2O, there's a 4. And I have run out of room. What am I going to do? I'm just going to continue on to the next line. Okay. And then once you get there, once you've found, what's the first thing you find? Moles. What's the second thing you find? Moles are the other thing. And then maybe you are asked to find a third, something about that other thing. Grams, volume, molecules. You just don't know, right? Like it could be anything. So at that point, you have to use your brain and say, I want to find grams because that's what the question asked me for. And that is grams of C3H8. Remember, every unit should have a species attached to it because this is stoichiometry. And we need to cancel moles of C3H8. 3 times 12 is 36 plus 8 is 44. Did I do that right? Let's see. Look, 44. Hey, look at that. 44.0 grams per 1 mole. Same mass as carbon dioxide. Weird. That's okay. And we do that calculation and we get, I'm going to cheat because it's right here, 61.1 grams of C3H8, and then we would be done. Is good? Do we feel like we need another example, or do we feel like we are good? Anyone want another example? Okay, in that case, there are some exercises here. How many are there? 1, 2, 3, 4. 5. Yeah, you can do all the exercises. Why not? So this is 7.1b. And I'm also going to have you read and make vocab list. So add on to your vocab list from before. For ivory book, so this is blue book. Pages. Where is my ivory book? There it is. my blue book? There's my blue book. Oh, and Emily needs a blue book. Thank you very much. And I need to give back quizzes. Where are the quizzes? Yeah. Call me over if you have questions. I'm going to try to mark these really fast for the people who just wrote today. We'll see if I can manage it. I'm not holding my breath, but we shall see. I do have it written down properly, but yeah. Whoopsie. Oh, thank you. Yeah, like right this moment? Well, we only have 10 minutes left. I think we can finish it in 10 minutes. I'm not staying. Huh? Yeah. So like, do what you will. I trust your morals. Quite frankly, at this point, a quiz mark is not going to change your grade that much, so I don't really care, but I also trust you. So. When you are ready. Okay? There you go. I have the quizzes. Try writing any of the different types. Okay, that's what I thought. I thought that was a forget not a. Hi. Junction. I can stay a little while. I'll stay for 10 minutes. It shouldn't take you that, like, that's just a short bit, right? It's different. Well, okay. I hear a lot of that, and I don't believe you guys. I believe you guys are quite smart. You just make some silly errors. That's okay. No, no, it does not. You did not understand what you were doing. If you didn't, oh, here's the best one. If you did not study and you did poorly because of that, that would count as stupid. Temporarily stupid, not necessarily long-term stupid, but it counts as a bad decision. Then you get to say, oh my gosh, that was dumb of me. Next time I better study.